Hello and welcome to T2 Day 1 of Honors Precalculus. We're going to start talking about, in more detail, the tangent function. So the tangent function, as you might remember, is sine over cosine. Another way to state that is y over x. So any coordinate, as we might remember right there, that's the coordinate xy. And we also know you can state that as cosine theta sine of theta, just like that. And the definition we're going to work with is tangent of theta is equal to sine of theta over cosine theta, sine over cosine, which is just going to be equal to y over x. So we need to make a graph and then state the period and where all the asymptotes are. So one way to talk about this is look at the easier points, the ones that work really well. We know right here when theta is 0, the point is 1, 0. So the tangent there would be the y coordinate over the x coordinate, so 0 over 1. So the tangent of 0 is 0. So we know it's going to be right there. So what's another nice point we could do? Well, we could do another nice point up here, and that's 0, 1. So in that case, tangent of 90 degrees, or pi over 2, is going to be 1 over 0. Well, that's undefined. So that means there's going to be a vertical asymptote at 90 degrees, So at pi over 2, there's going to be a vertical asymptote because you're dividing by 0. So we can go over here and we know at pi over 2, there's going to be a vertical asymptote right there. Well, let's go in between here to another nice point that I'm going to help you with. If you go to 45 degrees right here, so if you go to 45 degrees, you go to this point right there. That point right there is root 2 over 2 comma root 2 over 2. It's the same. It's the same x and y coordinate. Tangent is sine over cosine. So what that means is tangent of 45 degrees, which is tangent of, and remember this is going to be pi over 4, it's the same thing, we like radians, it's going to be 1 because root 2 over 2 over root 2 over 2 is 1. So right here is pi over 4, so we know it's actually going to be 1 right there. It's another nice point. You can also go right here all the way to 180 degrees right there. That's going to be negative 1, 0, and the tangent of pi, it's 180 degrees, will be 0 over negative 1, which is again 0. So what's going to happen here is the period here is actually going to be pi, because every pi it's going to be 0 here, 0 there, 0 here, and 0 again. So it's actually going to hit there. So what about this point right here down below? We have 0, negative 1, and that's 270 degrees. And the tangent there, the tangent of 270 degrees, which is tangent of 3 pi over 2, is going to be undefined again. It's going to be undefined again. So what that means is, oh, I didn't put that far enough over. This one goes all the way to here. We know there's going to be another vertical asymptote at 3 pi over 2 right here. So we have a vertical asymptote at 3 pi over 2, and we have one at pi over 2. Okay, so how do we put this all together? Well, let's get one iteration and then repeat it. So one way we can think of it as, what happens if we go down here, sorry, that's a little off, to negative 45 degrees. If we go to this point right here, you have root 2 over 2 comma negative root 2 over 2. So when you do the y over the x to get the tangent, the y over the x is just going to be negative 1. So that point will be right here. So now we actually can graph what this looks like. It's going to be a little spike going up like this and then down. And if you keep on repeating the same thing we just did, you'll get another vertical asymptote at negative pi over 2. And then this shape will just repeat itself. Be here and here, so it goes down. It's a little easier to see with this red ink. And you're going to have another one here at negative pi. You have these 3 points. It curves up, and then it curves down. So we have another vertical asymptote here. Didn't make this quite. Let's do it right like this. There it is, right like that. So this shape just gets repeated over and over and over again. You could draw this one, another one right here, part of it right there. And then over on the other side, it's going to be just this right-hand side of it. So if we wanted to know what the period is, we know it repeats every pi. So the period is pi. And it first starts, you could say at pi over 2. You could say it starts, if you wanted to, right at this one right here. And then it repeats every pi. So you would call plus pi k, where k is an integer. The next function we're going to graph is cotangent. Cotangent is the reciprocal of tangent, meaning cotangent of theta is 1 over tangent of theta. So we could just graph these points one by one and see what happens. One thing to know is that whenever tangent is 0, cotangent is going to have a vertical asymptote. So when we look at this, we have zeros at here, and at pi, and at 2 pi. So what that means is that vertical asymptotes are going to occur whenever tangent is 0. Tangent is 0 at 0, and at pi, and at 2 pi, like this. So that's where the vertical asymptotes are going to occur. We also know they're going to share certain points. So for example, 1 here, tangent of 45 degrees is 1. So cotangent of 45 degrees, which is pi over 4, we know is 1 over 1 then is 1. So pi over 4 is right here. So it's actually going to be just like that. That one point stays the same. That's this point, the point in blue right there. And then we can get the x-intercepts of cotangent for when cotangent again, I can do this out. Cotangent of theta is 1 over tangent, which is sine theta over cosine of theta. When you divide by a fraction, that's the same thing as multiplying by a reciprocal, so you end up with cosine theta over sine of theta. So you know that this is going to cross whenever cosine is 0. Whenever cosine is 0, that fraction will be 0. Well, cosine is 0, cosine is of pi over 2 equals 0, and cosine of 3 pi over 2 is 0. So we know it's going to cross here, and we know it's going to cross here, and we also know because this point, it's every pi, it's going to do that as well. So you can kind of see there for what this is going to look like. There's going to be another point here. You can plot 3 pi over 4 if you want, but you end up with a curve that just goes down like this, and a curve that goes down like this. And this just gets repeated over and over, so it'll eventually look like that. And don't mind the change in color. I just changed it to show left of the x-axis. So we know again the period is going to be pi, and in this case the asymptotes are going to be pi k, every multiple of pi. This one's every multiple of pi. This one above for tangent is pi over 2 plus pi k. So for question number 3, we're going to graph a tangent function where 3 things have happened. There's a negative 2 out front, there's a 1/2 in front of the theta, and there's a plus 1 here. So the plus 1's the kind of the cool one. We know it's going to move everything up. So in this case, like the midline, it's going to move everything up right here. So let's try to plot some points and see what one rotation of tangent is going to look like here. So you can just plot some points if you want to here. So you could do, what is f of 0? Plug in 0, you get negative 2. Well, 1/2 times 0 is tangent of 0. Tangent of 0 plus 1. Well, we know that tangent of 0 is 0, so this is just going to be 0 plus 1 is 1. So that first point will actually be right here. You could then figure out what the period is because you know the b value. Remember that? The b value in this case is 1/2, and we know that the period is equal to 2 pi over, excuse me, it's pi is the original, in this case, the original period of tangent. So for sine and cosine, it's 2 pi, but for tangent, it's pi. So what does that 1/2 do? You put the 1/2 down here, and therefore this is going to end up with 2 pi. So with sine and cosine, period was 2 pi over b. For tangent, it's going to be pi over b, pi over b. So in this case, it's 2 pi. So let's plot some other points here. Let's try plotting, I don't know, let's try pi over 2 right there. So if we do f of pi over 2, that's going to be negative 2 tangent of 1/2 times pi over 2 is pi over 4 plus 1. And tangent of pi over 4, we remember this right here. This is just 1 because tangent, sine of pi over 4 is root 2 over 2. And the same is for cosine. So this is going to be negative 2 times 1 plus 1. And this is going to be negative 1. So this will be down at negative 1. And if you do f of negative pi over 2, you end up with 3. If you do that out, you end up with 3. So you can figure out where the asymptotes are by figuring out where this is not going to be defined, where this function isn't defined, and that's actually going to happen when theta is equal to pi. If you plug in pi into this, you end up with f of pi is equal to negative 2 tangent of, in this case, pi over 2 plus 1. Well, this is sine of pi over 2 and cosine of pi over 2. But cosine of pi over 2 is 0. That is 0. You can't divide by 0. So there's going to be a vertical asymptote right here. So it seems like we don't have too much, but we actually have everything we need. We know the period is 2 pi because it's going to be pi over 1/2, because tangent period is pi, and that 1/2 just makes it twice as wide. So it's going to go, if it's pi there, it's going to be negative pi here. So what happens? It ends up looking like this. Now we know that tangent just repeats itself, so what you can do is just replicate this over and over again. And I didn't do it this time, but you can copy paste on your surface and get the same nice curves. But just pi, you end up repeating every 2 pi. For question number 4, this is one you can do on your own if you want more practice with the translation. It's very similar to what we just did. So next, let's look at the idea of invertible functions. An invertible function, a function is invertible if its inverse is a function. And this is where we talk about the horizontal line test. So when we've graphed sine, we know it starts at 0 and then it continues like as follows. Now, does this pass the horizontal line test? It doesn't. There is a horizontal line. There's actually a lot of them that pass through more than one point. So this is not 1 to 1. So therefore, that's what these 3 dots mean. Therefore, not invertible, meaning its inverse is not a function. Its inverse is not a function. The way we can get around this is by limiting the domain to force a piece of it to be invertible. And we're going to do that by looking at just this section right here. If we look at just this section right there, just the green, you limit the domain, and we'd be limiting the domain from negative pi over 2 to pi over 2. Just that green part does pass the vertical line test, horizontal line test. You see all these horizontal lines? They only cross once. And that would be the domain. And the range for that piece, it goes all the way from -1 up to 1 inclusive. So we're just looking at a piece of it, just that piece. So what we're going to do now is graph arc sine, which is the inverse of sine. This is how you write it. It's 2 different ways. When I was in high school, I used that a lot, but you can write it like this as well. They're the same exact thing, just 2 different ways. And what we're going to do is take sine from negative pi over 2 to pi over 2, and we're going to just flip. We're just going to flip the x and y values. We're going to flip the x and y values. So what that means is every point here, let's call, for example, 0, 0. If we flip 0, 0, it stays at 0, 0. That point will stay right there. Here, this point right here, that's the point pi over, that point right there is pi over 2 comma 1. So if you flip those, you get 1 comma pi over 2. 1 comma pi over 2 is a little bit more than 1.5. It's like right up there. So then if you do the same thing in the other direction, -1, negative pi over 2, which is right about here. If you graph more points, you end up with a curve that kind of looks like this. It kind of looks like the cube function, but it looks like this. So this right there is y equals sine inverse of x. It's the opposite, it's the inverse function of sine, but we have to do it only on a piece of the domain. Now for this one, the domain for this one, it goes from -1 to 1. In the range, it goes from negative pi over 2 to pi over 2. You might remember that the domain of the inverse is the range of the function. The domain of the inverse is the range of the function. So this right here was the range of the function. And this was the domain that we had to pick. So we can do the same thing. Same thing for cosine. We know that cosine starts at 1 and it goes down. It goes down like this, and I'll graph the whole thing for you. And those are those nice points, but now you just connect them with lots of curves. And this is not invertible because there are many horizontal lines that pass through more than one point. And what we're going to do instead is we're going to look at one piece of this function that is from 0 to pi. So just that green part. If we just do that green part, it passes the horizontal line test. All these horizontal lines pass through only one point. So the domain we're going to use is 0 to pi. And the range for there is going to be -1 to 1. So if we do the same thing we did before, where we graph, we just flip x and y coordinates. So for example, cosine of 0 was 0, 1. The inverse cosine, arc cosine, would be 1, 0. So it's going to cross right here. And then where is it, what does it do in between? Well, if we plug in, if we plugged in pi into this cosine equation, we know pi goes down to -1. So let's flip that and make the x -1. So it's going to be -1 pi, which is like 3.14. It's right about here. So what about in between? What about right here at pi over 2? We know at pi over 2, the cosine function is 0. So 0 pi over 2, it's right about here, a little bit higher than that. So what does this end up looking like? If you plot a few more points, you end up with this curve right here. So this right here is cosine inverse of x, the inverse cosine function. So if you were to do the domain of this function, it is from -1 to 1, which was the range of the original cosine function. And if you want the range is the domain of the original, which is 0 to pi. So if we do the same thing for tangent, we notice immediately that it is not invertible. But if we look at just the central curve here, that piece is invertible because every horizontal line passes through just one point. So the domain we're going to work with there is going to be, the domain will be -pi/2. It doesn't include it because tangent isn't defined at -pi/2 all the way to pi/2. And in this case, the range goes infinitely down and up, so -infinity to infinity. Now, if you flip this, if you switch x and y, for all of those coordinates on the green part of the curve here, if you switch x and y for all of the green coordinates of the curve, this is what you end up with. You end up with this function right here, which is arctangent. It's one of those curves flipped 90 degrees. It's pretty cool. And it goes again from -pi/2 to pi/2 because that's the domain of the original. Now it's the range. And now the domain of this, it keeps on extending infinitely out. So the range is actually all real numbers. Now what we just came to conclude here is that sine inverse, arc sine, gives an angle on the interval -pi/2 to pi/2 whose sine is x, Similar for cosine and tangent. So the way I like to think about this is, for example, sine inverse of pi, let's say sine inverse of 0. This means the sine of what angle is 0. The sine of what angle is 0. That's the statement you're going to say over and over again. Similarly, I could ask you tan inverse of 1. That means the tangent of what angle, is 1. The tangent of what angle is 1. So for example, when it says sine inverse of √2/2, this means the sine of what theta value, what angle is √2/2. And if you know your unit circle, you know that that's going to be this coordinate right there, which is pi/4. I'll try to clean that up a little bit. But this is saying the sine of what angle is √2/2, and that's going to be 45 degrees right there, that angle right there, which is theta equals pi/4, 45 degrees. But we like it in radians, so this is going to be pi/4 because the sine of pi/4 is √2/2. Now what about -1/2? For what angle is the sine -1/2? What angle has a sine of -1/2? So remember, sine is the y coordinate, so -1/2 is going to happen. We draw this out, it's going to look like on the unit circle, where is, that's not even close to a circle, that's pretty bad there, isn't it? So if you have a circle here, the y value has to be -1/2, so if this right here is 1, -1/2 is, so you're trying to remember what angle this is right here so that the y value is -1/2. And you might remember that that theta value would therefore be -pi/6, -30 degrees. So in this case, it's going to be -pi/6. You'll also remember that over here is also a potential answer. That right there would be this angle right here. So another way to say that is you add pi/6 to pi, so you get pi plus pi/6, which is 7pi/6. So then here you're asking for the cosine of what angle is -√2/2. So the x coordinate on the unit circle, when is it -√2/2? So that's going to be right there, this angle right there, this angle right there. So it's going to be 3pi/4 is this point right there, because the x coordinate right here is -√2/2, is -√2/2. So that's 3pi/4 right there. This one's a little trickier. It's the tangent of what angle is √3. The tangent of what angle is √3. So if you do the unit circle here, we know that tangent is sine of theta over cosine of theta. So when is sine over cosine equal to √3? So if you actually play around with these coordinates here, you'll remember this triangle right here, if that's 60 degrees, so pi/3, if you do with pi/3 right here, the coordinates are an x coordinate of 1/2 and a y coordinate of √3/2. So if you do the tangent of pi/3, that's going to be root 3 over 2 over 1/2, which is root 3 over 2 times the reciprocal. So the 2's cancel and you're left with root 3. So this is actually going to occur when you're at pi over 3. These doing inverse trig values are easier as long as you've memorized very, very well the unit circle values, the unit circle. So how do you work with these when they're nested together? Well, you do the inner one first. This says the sine of what is 1/2. The sine of what angle is 1/2? Well, the sine of pi over 6 is 1/2. So this right here is pi over 6 because the sine of the sine of pi over 6 is 1/2. So now you're doing cosine of pi over 6. So that is the excuse me, the x coordinate on the unit circle of pi over 6. So that's 30 degrees. That x coordinate right there is going to be root 3 over 2, and the height is 1/2. So in this case, it's going to be root 3 over 2. We'll do one more here. Cosine of pi over 3. We do the inner one first. Cosine of pi over 3. And that's just going to be 1/2 right there. The x coordinate of 60 degrees. So then you do sine inverse, which is arc sine of 1/2. The sine of what is 1/2? The sine of what is 1/2? Well, it's the sine of pi over 6 is 1/2. That's the y coordinate of 30 degrees right here. The y coordinate is 1/2 of 30 degrees, which is pi over 6. This just takes practice, and you need to know your unit circle. And part C and D you can do on your own for practice. The last part here is algebraic expressions. So what does this mean right here if we wanted to evaluate this? Well, sine inverse of 2x. That means the sine of what is 2x. So if you have a triangle, remember that sine is opposite over hypotenuse. So for this angle theta that we're trying to find here, the opposite over hypotenuse is 2x. The opposite over hypotenuse is 2x, so you can write that as 2x over 1. So the opposite side is right here, so that's going to be 2x, and the hypotenuse would therefore be 1. But if this is a right triangle, we can figure out what the base is with the Pythagorean Theorem. Let's call that a. So we know that a squared plus 2x squared is going to equal to 1 squared. So a squared is equal to 1 minus 4x squared. So a, the length of the base, is equal to the square root of 1 minus 4x squared. And we take the positive because we're only interested in positive lengths. So a is the square root of 1 minus 4x squared. Now, if that's what this value is, the green value there, asks us the sine of what angle is 2x. Well, this is the triangle right here. So now we do the cosine of this triangle right here. The cosine of that triangle. Well, the cosine, therefore, of theta is going to be the adjacent over hypotenuse, which is root 1 minus 4x squared over 1, which is just the square root of 1 minus 4x squared. So what you have to do is build the triangle. Let's do one more of these. So this says tan inverse of x squared. So if we have a triangle, tangent is TOA. Tangent is opposite over adjacent. So it's going to be opposite x squared over adjacent, which is 1. So now we need to figure out, let's say, the c value. So we know that c squared is equal to 1 squared plus x squared squared. So we know that c squared is equal to 1 plus x to the 4th. So c is equal to the square root of 1 plus x to the 4th. So now we're looking for, we know that c is equal to the square root of 1 plus x to the 4th. So now if this is theta, what's the sine of this angle? Sine is opposite over hypotenuse. So opposite over hypotenuse. So it's going to be x squared over the square root of 1 plus x to the 4th. And this would be your final answer. All of what we've done is a lot, and it takes practice. And the biggest thing you can do is work on memorizing cold the unit circle. This will take practice, and we'll do lots of it.